So we're about to begin Module 2.0 Advanced SIMPLIS topics. We'll start off looking at transient analysis, how to set up the settings for transient analyses. We'll look at a really important topic about how to set initial conditions that allow you to save an enormous amount of time during the course of a simulation project. The payoff, the big money topic in Module 2 here is how the periodic operating point really works. We'll look at both the overview, the core POP process, and then we'll look at what causes POP to fail and how to fix it. And you'll find this really helpful. And this will cover 95% of any issues with POP you might run into. And then we'll talk about managing simulation data. And our bonus topic for Module 2 is Chris Schwartz will be sharing with us some of the things that he's learned using SIMPLIS in system-level design applications. So you want to open up your Symmetric SIMPLIS Elements version 9.1. And we want to do here now is we'll open up the examples 9.1 folder. We'll open up the SIMPLIS folder. We'll go to Advanced SIMPLIS Training. And now we're going to go, yesterday we were working in Module 1. Today we're going into Module 2. All right. So you get that set ready to go. And then the other thing that we need to do is we need to open up our docs. Okay. So you can open up the doc several ways. You can go Help and click on SIMPLIS documentation, or you can go to the SIMPLIS documentation link that Matt put in the chat window. Okay. And so we'll go to Advanced SIMPLIS Training, and then we'll click on Module 2, which is called Advanced SIMPLIS. Okay. So these are the topics that we're going to discuss. We're going to go through, first talk about transient analysis settings, then we're going to do how to manage initial conditions, then we're going to do how POP actually works. Okay, so let's click on the first topic, 2.0, transient analysis settings. Okay, so what are we going to do? Well, we're going to learn how SIMPLIS saves switching instant data or topologies during the simulation. We mentioned that a bit in Module 1. We're going to go into a little bit more detail in Module 2 here. We'll determine what constitutes a new topology, and we'll also learn how to, basically manage all the settings for transient analysis, both the basic ones and then the advanced transient analysis settings. And then we'll talk about how this concept of forced new analysis, what it does, and how it actually disables the snapshots that we were talking about yesterday. Okay. So let's go with our first exercise. And what we want to do is open up schematic 2.1. So we're going to go Advanced SIMPLIS Training, Module 2 Examples, and then schematic 2.1. Yep. So we'll double click on that. And then we'll hit the home key and center our schematic. So what are we going to do here? Let's do, first we're going to hit, you can hit the function F8 key, or you can go simulator, choose analysis. All right. So let's take a look and see what we have. So now we're looking at, so we've clicked on the transient analysis tab, and we notice there's two boxes, two groups of parameters. One is the analysis parameters, and this is what SIMPLIS has to have. You need to tell SIMPLIS when we're going to start saving data and when we're going to stop the simulation. So the stop time is one critical piece. And then the start time is actually not start the simulation, but when is it that you want to start outputting data, right? When do you want to actually start saving data that you're going to send to the waveform viewer? Okay, those two pieces of information. The next box is, all right, when we plot the output data, what do you as the user want to see? SIMPLIS doesn't need this information to do all of its calculations and to do its calculations extremely accurately. So what we put in here is just allows us to get the fidelity of the waveforms to be what we need, okay? So in this case, we've asked for 10,000 equally spaced with very closely to equally spaced data points throughout, the course of the simulation. So that's what we're asking for. All right.
So here, Tom, when you say 10K points, you said they are evenly spaced, like a dot print on space?
Correct.
These
Correct.
are not raw data. Okay.
Right. The thing that we'll talk about and emphasize is this has nothing to do with the accuracy of the simulation. This only has to do with the fidelity of the waveforms that are output to the waveform viewer. So
Okay.
it's kind of how crisp or segmented are the waveforms, right?
I
And
see.
we'll do an example of that.
Okay. And when you run an FFT, then what
So
data block does it take?
okay, so here's the reason that we do this. Christoph, if you don't mind, will you ask that question in a few minutes? You'll see once we go through and show. I need to show what actually comes out, because the reason that we do this is some analyses like FFT, and possibly you may want to do some. You may want to export the waveforms and do some secondary analysis with some other tool. And that tool, for whatever the analysis might be, FFT is a good case in point, it requires equally spaced data points. So that's why we do this. SIMPLIS actually outputs something that's this plus. And so let's look at what it is. And then if you don't mind, ask that question one more time, because it's an excellent one. All right. Okay. So now let's cancel out the analysis window here. We'll just leave everything the way it was, and let's run the simulation. So you can run simulation either by going simulator, run schematic, you can hit F9, or you can hit the run button. Okay, and let's take a look at what we get. Okay, so we can see again, this is our buck regulator. We're looking at the output voltage, we're looking at the inductor current, and we're also looking at the switching node. Okay, so the switch node is right here. One thing you might notice, that is now in our later versions here, once we run the simulation, the color that's associated with each of these probes matches the color of the waveforms on the schematic. So it just makes it a little easier sometimes to jump back and forth. Okay, so let's just take a look and see what's happening. So if I click on the schematic and do Control Shift, it'll bring up my status window. And we talked about this a good bit yesterday, but we can see that we start off, and SIMPLIS has no idea what the circuit is. It needs to run through a few topologies before it finally finds one that satisfies all of Kirchhoff's current and voltage laws. And that's now we have a starting point is located, and now it just starts the simulation. And we notice there's two things. We see the percent complete. So this is a nice dot matrix output where we see percent complete. And by the time we're 1% complete, we've already encountered 17 new topologies. What is a new topology? Well, we remember from module 1, SIMPLIS is piecewise linear. So every model is a piecewise linear. So when the switch is on, it's an on resistance. When the diode is off, it's an off resistance. Even a nonlinear inductor is linear, it's linear at any moment in time. As the current increases or decreases, it may go from one piecewise linear segment to another. And just one thing I could maybe show is if you have a nonlinear device like in the inductor, well, what's that look like? I can right click on that and go to plot piecewise linear points, and it will plot out the piecewise linear characteristics of that device. So this is what we're actually simulating. So when I'm in the linear region, when I'm on any one segment, that is a piecewise linear segment that is part of it's a linear system. As the current increases, then we'll go transition from the topology associated with this piecewise linear segment to a new topology associated with this piecewise linear segment. So whether it's a piecewise linear resistor or capacitor, it all works. When we transition from one segment to the next, it's a new topology in the sense that it's different from the one we just had. So when we go to our status window, what is it? When we say new topology here, we mean this is a topology that in this simulation, SIMPLIS has not encountered before, okay? So at 1%, it's by the time it's gotten 1% of the way through the simulation, it's encountered 17 new topologies. By the time it's 18%, or let's say 19% complete, it's encountered 36 new topologies, but it goes from 19% to 100% and doesn't encounter any new topologies at all. Okay, so every time it's going through all kinds of topologies as it goes through the simulation, it's just it's not encountering any ones that it hasn't already encountered. So
if you
yes,
limit the number of segments for any components, like if you, let's say, simulate or model a diode with only 2 segments rather than
yes,
3 or 4, will it automatically reduce the amount of iterations?
yes, it will.
Okay.
What it'll do is it'll reduce the amount of new topologies, which will mean the computational load that that SIMPLIS has to go through is substantially less. So you're lightening SIMPLIS's load. So that's why when you do, like here, when we do the inductor, the art of SIMPLIS modeling is what's the least number of piecewise linear segments that I can get away with that will still give me my required accuracy. So I don't want to compromise accuracy, but what you'll find is in terms of, let's say like a Bode plot, the Bode plot accuracy is fairly, if you're going to operate up at 10 amps, you need to model this. This segment needs to be in play because this inductance is a lot different than this. And you'll see that in the AC analysis. Okay. But will my Bode plot, will it be a lot more accurate if I say had 10 times the number of segments? And the answer is no, it wouldn't. So getting the sense of how many piecewise linear segments do I need, what's the minimum number I need to still get very accurate results? That is kind of the art of piecewise linear modeling, but you figure that out pretty quick. And that's why when we have, so like when you put a diode on the schematic and, we say, you need at least 2 segments, on and off. We typically, as the default, kind of recommend 3. And there's reasons that we don't need to go into on that. But having a little bit of the knee modeled is very helpful. Very helpful. And so, and Ron, you might want to just say a little something about that knee in a diode model. Let's see. I think if we do, I think I can. Let's see. If you have a really, like, one of the things that people tend to do, which is a little unfortunate, is they'll tend to want, say, like with the off resistance to be really high. There is no diode on the planet that's actually 100 meg off resistance. So but they'll say ideal means no current whatsoever. So if they could put a gig ohm here, they would happily do it. And then on resistance of 1 micro ohm. When you have an abrupt corner like that in a 2-segment piecewise linear diode, for example, where you're switching, the slope is changing by 10 or 12 orders of magnitude, that can cause some numerical challenges for SIMPLIS, because then just a little bit of numerical error can say, oh, SIMPLIS wants, I want to be on the on segment, which is nearly vertical. And then, you go there and a little bit of noise says, oh, no, I want to be on the off segment. So so our kind of compromise here is, if you, if we go with 3 segments, then there's a more reasonable transition. And so people hurt themselves less often, shall we say. But if you're careful, you can do a 2-segment diode and you will, if you think about it, it's every combination. So every combination of these piecewise linear segments, this piecewise linear segment, these piecewise linear segments that you actually encounter in the circuit, is a new topology. So it's not like, well, this is 2, this is 2, this 2, but it's all the different combinations. And so, yes, you want to reduce the number of piecewise linear segments as much as possible, but still getting the required accuracy. So like, Christoph, in your example yesterday, where you're using piecewise linear resistors to generate a multiplier, more piecewise linear segments gives you more accuracy, but in terms of just the pure multiplier function. But you can see how you're creating loads more topologies for your system. So, and the more complex the system is, then adding a diode with 10 piecewise linear segments can really, make things go crazy. All right.
Exactly. Well, there's one application, for instance, where it's important to have perhaps more segments. If you have a flyback converter with multiple outputs, and then you do regulate on one of the outputs, the theory tells you that you're going to reflect the other capacitance from the other windings, scaled by the turns ratio square, to make a single output winding with, let's say, all capacitors and resistors collected on the same point. And when you do that, you assume that the dynamic resistance of the diodes is actually almost equal to 0, which is no longer the case when you go into light load conditions. I've seen instabilities like that. So it's good to at least make sure you mimic the dynamic resistance in high load and light load as well,
right,
so that it works okay.
And one of the things that we do to try to make that a little less of a challenge is, when you extract this, you can say, all right, well, let's, in this case, let's say 200 milliamps was kind of, well, this isn't a really great example, but let's just suppose. So, but I could set this for my full load case, for example, and it's going to be good down to half or third load. But if I really, really need to be accurate in my light load, let's say for purposes of, some AC analysis, or I want to look at some dynamic response, I can just re-extract this at light load and come up and get a new model at light load. And once you get, like with DVM, you can automate the process so that with DVM, you can tell it, okay, I need to extract. That is a very advanced capability right now. You have to really, really know what you're doing, but the concept is valid. So same with the MOSFET. Typically where I tend to get in trouble is around full load. So I want to have a good model, for full load, which will end up being a good model down to about third load. But if I really need, and I'm very concerned about, or I want to see, hey, am I going to get in trouble at light load? Then I would want to extract my MOSFET model for a light load condition, and then do my analysis there.
Okay.
But yeah.
I can see in the diode, for instance, in the pull down menu for the SPICE model, you have 184848, 14148, which is not really a power model. Does it matter? Okay.
Well,
no, I mean, in the schematic, if you double click on the diode, you can see that.
Yeah, this is
okay,
it's a tiny thing, right? So
okay.
yeah, in fact, yeah. So, but you can go here and select, and this is the whole diode. So there's 300 diodes, 400 diodes, in the models. But again, we'll never have the latest, greatest one that you want to use. So we make it easy to import those, and so that they are in our, your local copy of the library, and then we can do an extraction. And then for diodes, they're easier to model, even by hand, but it's super easy to put them into the library and then extract one that lines up with the one you're going to actually use.
Okay,
for sure.
So it means here it's going to extract the segment at the forward current that you specify.
Well, right. So
okay.
if let's do this. Let me go to, no, that's not what I want. I want this, 3 segments. So if we extract, so it's going to do this. Okay. So what it's going to do is we specified 200 milliamps, and it's going to go down to about half of that and draw a straight line there. And so in this neighborhood, about 20% is where you're going to often see more error. And similarly, when we're getting down more in the neighborhoods of 1%, you'll see some more error. But if, let's say that, wow, I want to see what's going on at 10 amps. That's what I really care about. Then let's do the same thing, but let's see, what was this? This was at 10 amps. Okay, this was 10, 10 milliamps. So 10 milliamps is what I really care about. So I'm going to go here and put in 10 milliamps, do it again. Okay, and now, so now I'm going up to 10 milliamps. If I just take this curve, I'm going to copy that and go back to this curve, which goes up to here. And okay, so now let me do this and make it a different color so it's easier to see. Okay, so now if we zoom in, so this is my new model. So the red, maybe pink was a bad choice. But the red is the SPICE model. And the nice thing about the SPICE model is, it's trying to model the physics. So it's good over a really wide dynamic range, including temperature, right? But here with SIMPLIS, in order to kind of do this trade-off between how many piecewise linear segments, how accurate am I, we have to do a little more work so that we can get the speed and still have the accuracy. And so this is the piecewise linear. So you can see it's a good model down here. It's good. It doesn't have near the error that we would have with our original model. So that's how we kind of address the fact that the model isn't the greatest over the whole range. Sometimes you'll need to do that. And then with temperature, you do the same thing, except then you'd see the whole curve shifts, right? But that's how we would suggest you handle those kind of things. So at any one simulation, we're managing the complexity, but we're still getting the accuracy that we need. So we've talked about new topologies, but when we re-encounter this topology number 28, it's no longer new. And so now it's called a known topology. Okay. And so the known topology is stored in memory. When we encounter it, we don't have to do the math overhead that we have to do every time we encounter a new topology that we haven't seen before. We just pull it out of memory and run and gun.
Tom, may I ask a
Yes,
question exactly
certainly.
to that topic?
Mm-hmm.
When I run many topologies, at some point it tells me there's a memory reallocation,
Right.
and then it starts to count from 1 again. Does it mean all the topologies get erased and
Right.
started over?
Some systems are so complicated that the benefit of SIMPLIS remembering the topologies is kind of lost. There's so many new topologies, and at some level, how often are we going to run into them again? That benefit gets diminished. And so because we're storing them, we're starting to use memory. So depending on how much memory you have and stuff like that, when we get close to having a memory issue, then we flush, we basically say, you know what, we're going to just get rid of all of these things that we learned now, and we'll start all over again. So it does start again. It starts all over. And so
if I double my RAM, it would essentially go further.
It's more limited by the addressable space on the program. So at that point, you cannot address anymore. You can add more RAM, it would not be able to take advantage of it. So, but once we migrate SIMPLIS to, right now SIMPLIS is still a 32-bit program. Once we migrate to 64-bit program, then yeah, adding more RAM would definitely alleviate the problem. I won't say eliminate, it would alleviate the problem.
Right.
Thank you, Ron.
Yep. So that's on our list of improvements.
So Thomas,
yeah,
I was wondering if I could ask a couple of things.
Sure.
The first thing I wanted to ask is related to when we've been running the simulations and you were showing the status window.
Yep.
You always see the message where it's launching the simulation, and you see starting point is found, right?
Right.
And then it launches the rest of the simulations.
Right.
Now, for users who are maybe not, they're new to SIMPLIS, I wonder if you could maybe discuss a little bit about common causes of a no starting point found
right.
error.
So
and then the second thing I wanted to ask about, so I don't take too much of your time, is that when you're doing the modeling of the diode, one nice thing, I don't know if you can do this in SIMPLIS or not currently. I wasn't able to figure out how to do it, but if I have a schematic that I may be using in Symmetrics, where I've made some models of the diodes in the local copy, in other words, I've modified a model, a SPICE model, and I've saved it locally to that schematic. It's a local copy. And if I wanted to copy that diode and put it in a SIMPLIS schematic and be able to extract the modified model that I made, can you add a feature that would allow the extraction?
Yeah, I think what you
copy?
would do, yeah, exactly. What you would do in that case is take your modified SPICE model and give it a unique name. Don't call it a 2N2222, or well, a 1N, whatever. Call it, dash Chris. So give it a unique name and then put that into your SPICE library.
Yeah, that's what I know. I can do that. I did.
Yeah,
I was
and
hoping,
that works quite nicely.
But I know, but I may not want anyone else using it, or I might have made it for a specific reason that I may only be modeling a few things, and I might be making the diode be unusable for other applications. It's like an ideal part, for example, or I may have modified something else that's not realistic.
Right. But that's
there a
why I'm
way to-
saying if you give it a unique name, then you're not going to accidentally use it, and nobody else is going to have it unless you give it to them.
Okay.
To
So
be
that
able
would
to,
be so that's the way to do it. Okay.
I think so. Yes. And what was your first question?
About the starting
Oh,
point.
starting point. Okay. So one example, think of an RC oscillator. So you have an op amp and you hook it up with positive feedback. So you have a capacitor and it's just oscillating back and forth, right? If you do not give that capacitor an initial condition, then every time SIMPLIS goes to try to solve the starting point, because you have positive feedback and there's no energy storage in the equation, it will, it'll say, oh, the oscillator should be high. It solves for that. But then, if the capacitor doesn't have initial conditions, oh, no, the output should be low. And then then SIMPLIS makes it low and it's, oh no, it should be high. So there's no solution. And like I say, SIMPLIS is very conflict averse. It doesn't like to resolve conflicts. So here it's got a circuit that no matter what state I put it in, it says I should be in a different state. As soon as you give that capacitor initial conditions, then everything's fine. SIMPLIS just happy as a clam and charges ahead. So it's typically, if SIMPLIS complains about not being able to find an appropriate starting place, it's typically because you need to set some initial conditions, usually capacitor voltages somewhere. So you just look for something that, okay, if this is truly an open circuit, is it even possible to find, a starting point? And if you go with that mindset, you'll dig it up.
Or if you
real
maybe
quick.
assign the wrong voltage to a feedback loop component or something to that effect, right?
Sure,
Where you
you
could
can.
saturate the error and without knowing.
Yeah, I'm not sure. So if you have, it's tricky.
Well, one thing that I think we need to bear in mind is, unlike SPICE or Symmetrics, SIMPLIS allows instantaneous switching. That for the classic logic gates and the switches. And so what Tom described on the oscillator happened because the switch is allowed to go instantaneous switching according to what the control voltage is. But if the control voltage is not initialized, then it could go not able to find the starting point. Another possibility would be a classic logic gate where by mistake you somehow, through several paths, an inverting signal is going back to your input. And so you end up in a loop that you will never get a correct state to start out. So one possibility would just simply put that would not work. That would not yield a starting point. Would be you put an inverter and put the output of the inverter back to its input. And because it allows instantaneous switching, you will never find any starting point.
Right. Okay, so let's keep cranking here. These are great questions, though, by the way. And we probably should try to have a little session just on starting points at some point, because it's not complicated once you understand what the problem is that SIMPLIS is struggling with. Okay, so let's go now and we'll close the status window. We're going to close the waveform viewer and we're going to close our schematic. And like before, whenever it asks if we want to save before closing, we always answer no. All right, and let's go to schematic 2.2. And in this case, we want to go 2.2 AE, PFC critical conduction mode. Hit the home key. And so let's do this. So if you didn't close your status window, hit Control C, Control Space, and clear it out. but I closed mine. So close the waveform viewer, and then let's go to F8, simulator choose analysis. And let's look at things here. Okay, so right now we have a stop time, 40 milliseconds. We're going to start saving data at t equals 0. We're going to do 10,000 points. It's just a transient. And we have forced new analysis check. So let's run the simulation. We'll just click the run button from here. Okay. So this is our PFC circuit. We're looking at the feedback signal, the soft start signal, and the control voltage. It's the output of the error amp that goes into our constant on time modulator. So that's what we're looking at here. So here's our soft start, the control voltage, and the feedback signal. Okay. All right. Now, SIMPLIS automatically, nothing you can do about it, saves a snapshot of this whole system at t equals 0, and the t equals the stop time. Automatic, it's just is what it is. All right. So what we can do is, so it's particularly when you're trying to get a circuit up and running for the first time to really get everything working, you don't want to do a 5 millisecond run and you've got omega hertz switching frequency, and you don't want to sign up for thousands of switching cycles when you start the simulation if you're not sure you got everything just right. So here I want to look at my PFC while it's starting up, look at a few critical systems and make sure, does this make sense? Does this make sense? All right. So we just did 40 milliseconds, and notice we're going multiples of 20 milliseconds, which is the period of our 50 hertz line voltage. Okay. So now what I'd like to do is, all right, I want to keep going, and maybe I want to go up to 100 milliseconds now. So what we're going to do, so let's go to F8, simulator choose analysis. And so I have a snapshot at the stop time. So I'm going to cut and paste. So I'm going to start now saving data at 40 milliseconds. And I want to go now to up to 100 milliseconds. Okay. And the other thing that I want to do, so this is a key new item here. I want to uncheck force new analysis. Okay. So you got to make sure you get this right. So make sure you uncheck force new analysis. What's that going to do? Well, when I have it checked, so don't let me forget to uncheck it. When I have this checked, what that tells SIMPLIS is, we don't care what you know about this circuit. We want you to pretend that you know nothing. So just get that out of your mind and do a new analysis as if you've never seen the circuit before. In particular, it's saying, even if you have a snapshot that's valid at 40 milliseconds, don't use it. Okay. Well, and so you'll notice for a lot of our training course stuff, we have force new analysis checked. The reason is because we want everybody to get the same results. Okay. And so this puts everybody, okay, we're starting from scratch as if we've never seen it. But when you're actually running, doing your work, typically you don't want this checked, because you want to say, hey, if you know anything about the circuit that can help me and make things go a little quicker, use it. Okay. So make sure that's unchecked. So we're start saving data at 40, we stop at 100, and let's run the sims. Okay. So now we'll look what happens. We started because we picked up that snapshot at 40 milliseconds, and now we just started going, and it is a perfect match, because when SIMPLIS does a snapshot, it remembers everything about the circuit. Snapshots are time dependent. That snapshot is valid at 40 milliseconds. It's not valid for any other time. It's also not going to be valid if you've made any changes to the schematic, if you've made any component changes, if you changed any of the sources, any change that you make, material change to the circuit. I mean, I could move something, I could adjust a position of things. But if I change the interconnect or I change values, SIMPLIS will say, well, I have a snapshot, but it's no longer valid. Okay. But in this case, we didn't change anything. Except we said we wanted to start now at 40 milliseconds, and away we go. Okay. And if I control space, go to my status window, notice it says right here, reading the state snapshot of the system at t equals 40 milliseconds. Okay. So it tells you that's where I picked this up. I found this is good. Boom. And away we go. Okay. Let's just so we see this is a really powerful thing, because often when you'll have a complex system and you want to, let me check, see, okay, everything looks good. Let's go a little further. Okay, now I want to take bigger steps. So maybe I'm taking 100 millisecond steps now, or 200 millisecond steps, but it lets me, I don't have to commit further than I want to, as far as just waiting for things to get done. And it allows me then to pick up right where we left off and continue on as I want to. Okay. So snapshots are powerful, and there's no reason not to ask for them. Okay. But when you check the force new analysis box, it is going to tell SIMPLIS, even if you have a valid snapshot, don't use it. Okay. One of the things, if you just think about it, if you run a pop analysis, say, I do just pop, my snapshot at t equals 0, because remember, it's going to output 3 or 5, whatever I've asked for, cycles of steady state. I have a valid, my snapshot at t equals 0 and t equals the end are steady state solutions. So the next time I run pop, if I haven't changed anything other than maybe, now I want to do AC, SIMPLIS is going to go, oh, I have a valid, snapshot. And what do you know? It's already in steady state. So that's why sometimes you'll see the second time and the third time I run this simulation, maybe I said, oh, I needed to add a probe or something. The next time I run, it's like, oh, you're good. It's a lot faster. So there's no reason not to take advantage of the snapshot. Okay. Now, let's just take a quick look, and we're going to do this very fast. Go back to F8, choose analysis. There's an advanced button, so we're in the transient tab. And so you can actually enable extra snapshots, and the documents here tell you how to do that. So we're not going to go into that, but it always automatically has a snapshot at t equals at the beginning and at the end. But you can actually enable snapshots to happen in between by making this a non-zero number. Okay, and you can read the docs for that. Okay, so SIMPLIS saves the switching instance data. Every time there's a topology change, it's saving the information about that topology, and it's basically learning your circuit, all right? If you have a really complicated circuit with an enormous number of topologies, SIMPLIS learning, it kind of diminishes a little bit the benefit of SIMPLIS learning things, but it's very, very circuit dependent, but it can diminish that benefit a little bit. You'll often see that the new topologies are concentrated towards the beginning of the simulation time. Okay. And so let's see. So in force new analysis, like I said, says, forget anything you know about the circuit. Pretend this is the first time you've seen it. But enabling snapshots, having snapshots go is almost always good for you. It's never bad for you. Okay. All right. So we'll cancel out of that. And so our next topic is going to be initial conditions.